Hello. Oh, let's get started. So people may be still coming, so both remotely and to the classroom, but I think it's time. We are supposed to get started, so let's get started. So before we start, so I got a couple of questions in the last week, and I put some answers to those questions, and especially important one is so I guess Kawahara-kun pointed out that there was some typo or sort of mistake in the notebook I was distributing. So just check this, and it's kind of very basic and stupid mistake. So check this answer to the questions in the last week. So here's today's plan. So I will explain and demonstrate the notebook PD04, which was about CUDA scheduling. And after this, I'm going to revisit the last part of the last week's the lecture, which was about how to choose the appropriate block size for performance. So that the reason why I do this again is, so first, I think it's better to understand, easier to understand after seeing this demo. And the other reason was when I was speaking about this in the last week, I was a little bit lost. So I was kind of missing the point. So let me do it again. So the slides are actually modified slightly. And after that, I will get into another topic, which is SIMD programming. And if time permits, you have a chance to work on the notebook on SIMD programming. So let me start with the demonstration of this CUDA scheduling thing on PD04 CUDA sched.sos. So just to prepare, make sure we have the compiler in the past. So, okay, so we are playing with this simple benchmarking code, which is not necessarily doing a very useful thing, but very useful to understand how GPU actually operates. So, well, let me, so before getting into what this code does, just demonstrate how to compile and see what kind of output it produces. So these first two parameters give the total number of threads, which is 64 in this particular command line. 32 is, the next one is the number of threads in a single thread block. So it is a block size, thread block size. And the next two parameters, 10 and 100, actually specify how long each thread should run. So with that, let me get into the code a little bit. So basically, what the main function is doing is simply to launch the specified number of threads with the specified thread block size. So it simply passes the command line arguments. And okay, so it eventually runs this kernel, CUDA thread 1. And this is the number of thread blocks, which is computed by simply dividing the number of threads by the thread block size. And this is exactly the thread block size that is specified in the command line. And it gives to the next two parameters how many times each thread should do something. And let's look into this CUDA thread function. So how these two parameters are used. So each of these threads is doing is basically this loop. So it simply repeats so many times. So in total, n multiplied by n number of times. That's this simple multiply and add operation. And it is simply taking the clock. So it's essentially the time, from time to time. So more specifically, every m iteration, it looks at the clock, right? And it does so n times. And it also records this get SMA ID function is the function that returns which streaming multiprocessor this thread is running on. So basically, while repeating this AX plus B so many times, it checks the clock from time to time. It also records on which streaming multiprocessor this thread happens to run. Okay, so this is basically all these threads are doing. And it outputs something like this. So remember that, so 10 is the number of times the clock is taken, right? So it records the clock 10 times. And this is the 10 numbers. So these are, so these 10 numbers are exactly the recorded clock. So you get 10 numbers here, right? So this is all it does. And it also, so because you say, okay, you want to run 64 threads, each thread block having 32 blocks, the program says, okay, so you have 32 threads in each block and you have 2 blocks. So which is simply 64 by 32, or 64 over 32, right? And this is a small visualization tool. You don't have to understand how it works. And okay, let's simply do a very simple experiment in which you run only a single thread. Okay, so you only have a single thread and record the clocks. So actually 100 times this time. And this is the visualization. So what you are seeing here is actually the 100 dots. So maybe it's difficult to see from the distance, but you see 100 dots. And how many times did it take? So it's something like 700,000 clocks. So how many times you actually did this AX plus B operation? It is 100 by 1,000 times. So it performs X plus B 100,000 times. So 700,000 clocks is the time it took to perform AX plus B 100,000 times. So so the simple calculation tells you that a single X plus B took something like 7 clocks, 7 GPU clocks. Okay, so how much is it in terms of the performance? So 7 clocks. So a single FMA every 7 clocks. So let's say for the sake of simplicity of the calculation, the frequency of a GPU is 1.4 gigahertz, right? So 1.4 gigahertz means that it has, within in a second, in a single second, it performs 1.4 billion times. So the clock advance is 1.4 billion times in a second. And you do X plus B every 7 seconds. So the total number of FMAs this GPU can perform with a single thread is something like 200 million times, right? So in a second, the clock advances 1.4 billion times. And X plus B is performed every 7 cycles, right? So it performs 200 million X plus B's in a second, right? So it's something like 200 meg FMAs per second. So it's like 400 megaflops, 400 megaflops, right? So it's far away from the GPU's peak performance. Yeah, I think it's obvious to you that because I'm running only a single thread, but this is the performance of this is in a way the capability of a single thread of a GPU, which is very small compared to the total capacity of a GPU. So the peak performance of the GPU is something like 20 teraflops, something like 10 teraflops, right? So it's much more than the 1,000 times of a single thread performance we have just witnessed, right? So I'm going to play with this program, changing the number of thread blocks and the total number of threads, which is the size of each block. So this experiment, for example, so let's say you create in total 100 threads here, but you still maintain the size of a single thread block to 1, just as before. So it ends up creating 100 thread blocks, so each having only a single thread. So when you visualize it, so what does it look like? So it looks like this. So let me slightly increase this number for the purpose of explanation later. So let's make it 200. So you create 200 thread blocks, each still having only a single thread. So you see a clear pattern of the color. So by the way, the color indicates the streaming multiprocessor it happens to execute a particular thread on. So this y-axis represents the thread index. So in the previous example, you only have a single thread, right? And in this case, you have 200 separate threads. And it seems obvious that these threads are somehow distributed across many streaming multiprocessors, indicated by different colors. But one thing that is worthy of emphasizing is that the time it took is almost exactly the same as before. Right, so remember that it might sound obvious when you are thinking about GPUs, but it is still worth noting that this experiment has performed 200 times more work than the previous example, but the execution time was almost exactly the same as before. So both like to 700,000 cycles, right? And the other thing is, so these apparent patterns of the colors indicate GPU is doing something obvious and reasonable to distribute all threads to different streaming multiprocessors. So how many streaming multiprocessor do you think this GPU has? When you look at this pattern, you may be tempted to think that, okay, so this is where each streaming multiprocessor gets exactly 1 thread block. So it may be tempting to think that this GPU has something like 50 plus 54 or something like that streaming multiprocessor. But interestingly, actually, this is not the case. So the number of streaming multiprocessor this GPU has is actually 108, which is twice as many as 54 you are witnessing here. So actually, the truth comes out when you actually look at this text file. So let me get into the file itself. I don't know why it doesn't open. So let me do instead. Okay, so I'm trying to show the part. Sorry, this is okay. Yeah. So I'm trying to show the first 10 lines of this output. And okay, so this text file tells you so on which streaming multiprocessor this particular thread happened to run. And the first thread happened to run on the streaming multiprocessor 0. And where did the next thread run? It is in the next line. So the next one actually happened to run on the streaming multiprocessor 2. So slightly different from what you would expect, which is streaming multiprocessor 1, right? And the next one is streaming multiprocessor 4. So this seems how GPU distributes so many thread blocks. So the first one goes to 0, the next one goes to 2, the next one goes to 4, and after you get you dispatch a thread that goes to what is it? So 106. Then it comes back to the thread number. No, streaming multiprocessor 1. So it's like 0 to 4. That's 106, which is then 1, 3, 5, something like that. So this is the reason why you see this pattern that looks like the 54 distinct colors, but in fact they are actually 108 distinct colors. And so this color for streaming multiprocessor 1 is almost indistinguishable from the color of the streaming multiprocessor 0. So this pattern repeats, right? So this sort of suggesting, so it has 108 streaming multiprocessors, and GPU is dispatching a thread block to an available streaming multiprocessors in a very simple fashion. So let me do another experiment. So another way of changing the total number of threads. So this time, okay, so the last time I was keeping the thread size to 1 and only changing the number of thread blocks. So that's why you see these threads are executed on different streaming multiprocessors. But this time, so we change the total number of threads and the thread block size at the same time. So both are keep the same. So you in this case, you have 256 threads in total, but a single thread block has that many threads. So in this case, what happens is something like this. Oh, so let me okay. So let me fix the number of times to iterate. So let me iterate the same 100 times. So then, okay, obviously, so those threads this time are all executed on the same streaming multiprocessor because they are all in the same thread block. So this is how GPU operates. So as I explained before, the thread block is the unit of dispatching. So all threads in the single thread block always go to the same streaming multiprocessor. So that's the reason why you see only one color here. And so let me get back to n equal 1 case. Then you see something like this. And you increase the number of threads to something like 100. So the interesting is, again, so this time we are using only one streaming multiprocessor because we are using only a one thread block. Still, the execution time looks almost the same as before. So what does it indicate? So this is a single streaming multiprocessor, like I say, but still running 100 threads versus running only a single thread takes exactly the same amount of time. Well, remember that, so the amount of work is literally increased 100 times, but still the execution time stays the same. So what does this indicate? So this basically indicates even a single streaming multiprocessor has some ample parallelism inside. So it is capable of executing so many threads simultaneously. Simultaneously does not necessarily mean literally at exactly the same cycle. But the point here is that they do not run like, okay, so one thread completes and only after other threads start executing. This is not how the GPUs operate. So GPUs put so many threads on the same streaming multiprocessor at the same time and execute them concurrently. So simultaneously, meaning that, so they interleave, the executions interleave in a very fine-grained fashion. Like in a particular cycle, these threads run. And in the very next cycle, totally different set of threads run. So this is very different from how CPU operates, right? So in a CPU, on each virtual core, only a single thread runs at a time. But still, from the viewpoint of humans, they look like executing concurrently, but the actual interleaving happens in much more coarser grain. Like, okay, so a single thread runs for few milliseconds. After that, the operating system gets interrupted and interrupts the execution of the thread that was running and switch to another thread explicitly. So this happens in the software. GPU is different. So GPU takes so many threads by the hardware and interleave the execution of them in a very fine-grained fashion. And actually the other side of the same coin is that, okay, even though GPU has so many resources to execute calculations, a single thread alone cannot utilize all of them. So like we just witnessed, so even when you have only a single thread, a single AX plus B still takes something like 7 cycles, right? So what happens between those two back-to-back X plus B? Well, actually, GPU isn't doing pretty much anything. So it is just waiting for the previous, the result of the previous AX plus B to continue the next AX plus B. So by having so many threads in a single streaming multiprocessor, so it becomes possible for GPUs to execute. So these threads in this cycle, and in the next cycle, it executes different threads. And after something like 7 cycles, the same thread has another chance to run. So this is what is happening here. So interleave executions of so many threads that are individually very slow, where it takes something like 7 clocks just for doing a single AX plus B. But this is very interesting way of doing things fast by GPU. But actually, in later weeks, you learn that CPU is more or less the same. So CPU, even CPU, it is not totally different from GPU in terms of how they do so much work in the unit in the fixed amount of time. Okay, so I got a really good question on the chat. So if you increase the number of threads large enough, eventually it would take longer, right? So yeah, this is exactly right. So I think you get that point very well. So let's continue increasing this number. For example, 128. Well, it still takes almost exactly the same amount of time. But what if you increase it to 256? So it takes just slightly longer, right? And what if you make it even larger? I don't know if it is possible. So maybe it's not possible. So so there's some limit in the number of threads in the single block. So if you make it 1024, so if you compare this to the number you get with 256 threads, I think this time you see almost proportional increase. So the execution time increases almost a factor of 4, going from 256 to 1024. So this happens precisely because the GPU, even GPU, has only so many resources. So if we put threads more than the GPU is capable of executing, then yeah, essentially each of these threads gets slightly slower, or may even run one after another. Yeah. And so let me just calculate how close are we to the peak performance of the GPU. So let's put let's get this number back to 256, because this seems where the GPU is saturating. So these threads are saturating the capability of GPU. So going beyond 256, the execution time seems to start increasing. So this is a sign that GPU is pretty much saturated. So calculate how many flops all these threads perform together in this amount of time. So let's do a simple calculation. So we have 256 threads, each doing this number of FMAs. So this is the total number of FMAs they altogether perform. And from looking at the graph, actually, it took something like 900,000 cycles, right? So this is somewhere like 900,000 cycles. So this is the number of FMAs performed every single cycle on average. So you get something like 28. So what is actually the peak performance of a single shared streaming multiprocessor of a GPU? Well, it actually depends on the precision of the floating point numbers. So, but in this experiment, I'm using double precision numbers, and just like okay, like here. So we are using a variable of type double and doing all these computations in double precision. So the number of FMAs a single streaming multiprocessor can perform at every single cycle is actually 32. So we are pretty close to 32. And if you actually change the type of the double to float, which is single precision floating point numbers, the peak performance is actually 64 FMAs per cycle. And you get something like 56. So you can actually change the program by yourself and observe that you get something like 56 FMAs per cycle. So finally, you can multiply this 256 threads in each block. And for example, you can have as many as 108 multiplied by 256 threads. So it is creating 108 thread blocks, each having 256 threads. So this setting hopefully taps almost the peak performance of this GPU device. Well, actually, the visualization will take so much time. But actually, so the thing you want to observe in this experiment is the execution time. The total execution time is still in the same ballpark as this experiment. So a single shared streaming multiprocessor executing 256 threads. But this time, I'm simply doing the same thing on each of these streaming multiprocessor. So it's still trying to visualize it. I don't know whether it finally comes out. Yeah, it finally comes out. So the execution time, looks almost the same as before, right? But this time you are executing so many more threads, something like 250, sorry, 25,000 threads. So this is the capacity of a GPU. But one thing that I need to emphasize for the purpose of the following discussion, especially on GPUs, CPUs too, is a single thread does not run that fast, right? So what GPU is very good at is to run so many threads at almost the same speed as the case in which you have only a single thread. So this is the very reason why GPU is said to be very good at executing parallel workloads, right? But actually, we are going to witness that CPU is more or less the same, well, in principle. But the only difference is how you actually have the parallelism existing inside each core. So just remember, this is what GPU actually looks like, and this is how GPU operates. All right. So do you have any question at this point? Okay. So with that, so let me revisit the last part of the last section of this slide. So the question of this section was, okay, so this slide is slightly modified from the last week. So the basic question we want to be able to answer is, okay, so let's say we need to create 10,000 threads. So how should you divide them into thread blocks? So there are so many ways you can do that, right? So you can have only a single thread block that has 10,000 threads inside. Well, it is actually impossible. So there's some hard limitation about the size of the thread block, but just for the sake of discussion. So you could arrange things in this way, or the other extreme is, so like we did in the experiment. So you could have 10,000 different thread blocks, each having only a single thread. And there are so many ways in between, right? So which one is the most appropriate, well, in terms of the performance? So like the previous experiment I have just shown suggests that the goal is actually to run an enough number of threads simultaneously so that they utilize the hardware capacity of a single streaming multiprocessor. Okay. So this is a conceptual illustration. So each horizontal arrow indicates how a single thread progresses over time. And this star, well, just imagine that the star means a point at which thread does some useful work, like AX plus B in the previous example. And as I explained in the demonstration, so a single calculation actually takes some non-negligible amount of cycles. So it's not just that. It's not that the FMA operation you performed gets a result in the very next cycle. It takes much more than that, something like 7 cycles. So in between, this thread cannot do anything useful. So if you have only one thread in a streaming multiprocessor or whatever hardware resources you have, then hardware resources will be very much underutilized. So putting the next thread on the same streaming multiprocessor doesn't increase the total execution time at all. Because, well, so first of all, so the GPU has so many resources. And there are plenty of time between these consecutive useful operations in which some other threads can utilize the same resources. So even if the hardware resource is very limited, if each thread progresses very slowly, then it still makes sense to have so many threads on the fixed amount of resources. So like I said, so as the previous demonstration suggests, this is how the GPU gets performance. And so you like to have a situation like this. So individual threads are kind of slow, but you have so many threads that in total, the device is able to do so much more work in the same amount of time. Okay, this is the goal you want to have in mind when you decide which arrangement is best performing. Okay, so to this end, so let's understand what GPU actually does given a thread block size and the number of thread blocks. So this is what you specified after all, right? So if the GPU is given these two numbers, what actually happens? So this is the basis upon which we can reason about performance. So this is this slide is kind of revisiting what I explained in the last week, but just this is very important point. So there's is a hierarchy of parallelism within a single stemming multiprocessor that was thread. And so the thread is the sequential computation as you described as a kernel function in the CUDA program. And a group of 32 threads makes something called a warp. So a warp is always 32 threads. So there's no way you can change it. It is sort of burned into the hardware. And remember that what you specified is the size of the thread block. Actually, the thread block is the next level above warp. So for example, when you specify the thread block size to be, let's say, 60. So GPU divides this 60 by the warp size. And the calculate the number of warps that makes a single thread block. So for example, if you specify the thread block size to be 60, then the 60 divided by 32 is something like 1 point something, right? So you need 2 warps, right? So 2 warps makes a thread block actually. So this is what a thread block looks like. So it has some number of warps inside. And it's not that a single stemming multiprocessor is able to execute only a single thread block at a time. It is actually able to execute multiple thread blocks simultaneously on the same. So what is actually happening at runtime looks like this. So this is what is happening in each stemming multiprocessor. So remember this hierarchy of parallelism. Thread warp, which is 32 threads. Some number of warps make a thread block. Some number of thread blocks are dispatched into a single stemming multiprocessor. So warp, what is warp again? So warp is the unit of instruction execution. So how it is implemented in the GPUs is actually 32 threads in a single warp share a single instruction pointer. So all these 32 threads execute the same instructions at the same time. So in this sense, actually a warp in the GPU is very similar to a CPU thread executing 32-way SIMD instructions. So I'll get to SIMD things hopefully in the later of today. But I just briefly explained that this is this SIMD instructions that is able to do the same operation like addition or multiplication on a number of operands with a single instruction. So this is SIMD instruction. So in this sense, a warp is very similar to SIMD instructions in the sense that all these 32 threads need to do exactly the same instructions, exactly the same instruction in a single cycle. But this is what a warp is. So what happens at runtime is that at every single cycle, a stemming multiprocessor selects a few or actually up to 2 warps that are ready to execute and execute them. So it's not that, for example, a single stemming multiprocessor is able to, for example, execute these 4 threads from this warp, these 5 threads from this warp, and these 8 threads from yet another warp in a single cycle. This never happens. the only thing a single shared streaming multiprocessor is able to do within a single cycle is just to pick at most 2 warps and execute them. So in the best case, so 2 warps, so you have 64 threads. So if all of them execute FMA instructions at a particular cycle, then this is the maximum performance you can get, right? So this happens, if this happens every single cycle, this is how GPU gets the maximum performance. So at every single cycle, 2 warps execute. So all threads in 2 warps execute FMA instructions. So what is the implication to how you choose the appropriate block size? So it is that, so there's a rarity point in making the block size less than 32. Well, actually not a multiple of 32 as a matter of fact. So having a thread block size being, for example, only 1 thread, rarely makes sense. So it is simply wasting the remaining 31 threads in the warp. You actually need to have anyways. So similarly, but to a somewhat lesser degree, that it doesn't make much sense to, for example, have a thread block size of, let's say, 40, right? So you still need 2 warps. But if you have 2 warps, you can have actually 64 threads, right? So 24 threads are simply wasted if you specify the thread block size to be 40, right? So it is almost always a good idea to make the block size a multiple of 32, which is the warp size. And another thing that is not necessarily exactly the point of this discussion is, like I said, all these 32 threads need to execute the same instruction. So what happens if you have a branch in your program? Then some of the 32 threads execute then branch, and other threads execute else branch. So these then branch and else branch cannot be executed in a single cycle. So actually, when this happens, the execution of this particular warp takes twice as much time. So actually, the time to execute both then and else branch. So you'd better to maintain that all 32 threads within a single warp branch in the same way. So this is something called avoiding a warp divergence. Okay, so this is warp. And next, the thread block. So like I said in the earlier weeks, so a thread block is the unit of dispatching to a streaming multiprocessor. So when a GPU, for example, gets a kernel launch statement like this, so you create NB thread blocks, right? So conceptually, so you can imagine that these NB blocks make a queue. So each waiting for some streaming multiprocessor to execute. But the point here is that GPU dispatches to streaming multiprocessors 1 block at a time. So it always dispatches the entire block to a particular streaming multiprocessor. So it never happens that, okay, so 100 threads in this block will go to shared streaming multiprocessor 0, and the other 100 threads go to another streaming multiprocessor 1. So this never happens. So all threads within a single block go to the same streaming multiprocessor and execute it simultaneously. And the other thing is, so once a particular thread block starts running on one streaming multiprocessor, they stay on that streaming multiprocessor until it finishes. And meanwhile, it occupies registers and shared memory. So resources you need to compute. And throughout the entire lifetime, from the beginning to the end of a particular thread block. So this effectively limits the number of blocks that can simultaneously run on a single streaming multiprocessor. Because each streaming multiprocessor has only so many registers and only so much shared memory. And if a single block takes some amount of registers and shared memory, and they need to stay on that streaming multiprocessor from the beginning to the end, well, it obviously limits the number of thread blocks you can have simultaneously on a single streaming multiprocessor. So this is exactly what this figure illustrates. So there are some registers used by each thread. So this verb takes some number of registers, and you have some number of verbs in a single block. So this single thread block takes this number of registers. So illustrated as orange in this video. And you also specify, if you like, the amount of shared memory you want to allocate to each thread block, right? So the point here is, okay, each thread block needs to occupy some amount of registers and some amount of shared memory while it is running. And the streaming multiprocessor, so a single streaming multiprocessor has only so many registers and only so much shared memory. So this clearly limits the number of thread blocks you can simultaneously have on each streaming multiprocessor. So so a few words about registers and shared memory in case you are not very familiar with them. So registers generally hold the local and temporary variables of threads. So this is a very common concept in any computers. So no matter whether it's GPU or CPUs. So you need to remember values in variables. Right, so this is typically done by storing values in registers. And how many registers each thread need is something determined by your program, but more by the compiler. So how the compiler translates your program into machine instructions. So this is how the registers are determined. And shared memory is something you can explicitly specify when launching a kernel. So I think I have explained this before. So you specify the amount of shared memory needed by a single thread block. Right, so this way you effectively determine the number of registers and the amount of shared memory of each thread block. Right. So like I said, so because the hardware has only so many registers and shared memory, this limits the number of thread blocks that can simultaneously run at the same time. So what kind of hardware limits exist? So this is a case of 800 you are playing with in the Jupyter environment. So this is almost the latest version of NVIDIA GPUs. So it has 64,000 32-bit registers in each streaming multiprocessor. It also has shared memory of 164 kilobytes. So these are hardware limitations very relevant to the previous slide. Well, actually, there are two other somewhat more direct and straightforward limitations, which are, first of all, the number of works that can simultaneously run in each streaming multiprocessor. It is 64. So no matter how you reduce the amount of registers you use and you reduce the amount of shared memory you use, a single shared streaming multiprocessor can simultaneously run only up to 64 works. And the other thing is, well, it also has a limitation in the number of thread blocks that can simultaneously run, which is 32. So all in all, so this is how the GPU determines the number of thread blocks that will simultaneously run on a single streaming multiprocessor. So you are given, well, so from the perspective of GPU, so you are given the number of threads per block. So this is something that the programmer specifies when you run the kernel, right? So let's call it TB, the thread per block. You also specify the amount of shared memory per block. So all quantities per block are subscripted with this B. So SB is the amount of shared memory per block. And you also, so it is not necessarily you who specify the number of registers per thread, but indirectly you write a program and the compiler determines from your program how many registers are needed per thread. So let's call it R1. So the quantity per thread is subscripted by 1. Okay, so these are three parameters that you effectively specify as a programmer. So from the perspective of GPU, these are given quantities, right? So based on these given quantities, GPU determines the number of threads simultaneously running in each streaming multiprocessor. To that end, it first calculates, so it sort of translates resource requirement in terms of the resource requirement per block. So it first calculates the number of works per block, which is simply the number of threads per block divided by the warp size, which is 32. But divisions are performed with rounded up. So the fractions is taken as the whole unit 1. So you determine first the number of works per block, and you translate this registers per thread into registers per block by multiplying R1 by 32, which is the number of threads in the warp, and further multiplying it by the number of works per block, right? So this is the amount of the number of registers you need per block. So so this WB is, for example, in this figure 3, and registers per block is the area of this orange, and shared memory is the area of this green. So you get resource requirement per block, and you simply divide whatever the hardware limitations are by these numbers. So the number of blocks that can simultaneously run on a single streaming multiprocessor, let's call it MB, is simply this. So the minimum of all these 4 quantities, which is, so this comes from the register limitations. So the streaming multiprocessor has only 64,000 registers. So let's divide it by the number of registers a single block needs. So let's divide the shared memory per streaming multiprocessor by the amount of shared memory a single thread block needs. So this is 64 by WB is the limitation that comes from this one. So verbs that can simultaneously run. So if it is able to execute only 64, only up to 64 verbs at a time. And for example, each thread block has 3 verbs inside. Then yeah, you can execute only up to 21 thread blocks at a time, right? And 32 is simply the direct limitation that stems from this limitation. So you get all these 4 quantities and take the minimum of the 4 quantities, right? And the number of verbs that can simultaneously run. So I'm just translating the number of blocks into the number of verbs by simply multiplying the number of blocks by WB, which is the number of verbs inside a single thread block. So this is the formula that tells you how many verbs are running simultaneously on each streaming multiprocessor, given a specific configuration of register requirements and shared memory requirements. So the principle is very simple, right? But this slightly complicated. So what is the main takeaway? So what are often good thread block sizes, or conversely, what are the thread block sizes you better to avoid? Okay, so for a moment, let's ignore the first 2 factors. So that stems from register size and shared memory size. So take a look at only the 2 last factors. So if we ignore for a moment, and so the first 2 factors. So one possible guideline is to basically you want to try to run the maximum 64 verbs. So 64 verbs is exactly the limit predetermined by the hardware, right? So this is here, right? So the goal is to run 64 verbs at the same time. And this can be actually accomplished by the very but by having something very simple in mind. So one thing is that, so you take the minimum of these 2, right? So if WB is too small, so let's say 1, then this becomes larger than 32. But you still take the minimum of the 2. So you get only 32 thread blocks. And you multiply by 1, right? So you end up running only 32 verbs at the same time. So one thing is you don't want to make this to 1. So one rule of thumb is you want to put at least 2 verbs in a block. So just avoid thread block size smaller than 64. And the other thing is, so somewhat tricky, is that you want to choose the number of verbs per block that divides 64. So that this 64 divided by WB becomes an integer. For example, let's see what happens in an extreme case when WB is, let's say, 33. Then this becomes 1, right? 64 divided by 33 is 1 point something. And you cannot have 2 such blocks at the same time, right? So because this ends up with 66 threads, 66 blocks. So this cannot happen, right? So you only you are only able to run only one such thread block. So this becomes 1. And 1 multiplied by 33. So you end up having only 33 verbs simultaneously running at the running in a single streaming multiprocessor. So this something like this doesn't happen when WB precisely divides 64. For example, if you make it, for example, 8, then this is exactly 8, right? And 8 multiplied by 8, you get again 64, right? So the same thing happens when you have, for example, WB being 4, then this becomes 16. 16 multiplied by 4, you end up having 64 verbs, right? So the second rule of thumb is to choose the number of verbs per block that divides 64. So combined, often good numbers are like this. In terms of the number of verbs per block, it's going to be 2, 4, 8, 16, 32, or divide 64 precisely, right? So when you translate it into the thread block size, the number of threads per block, then it's going to be 2 multiplied by 32, which is 64. So 64, 128, 256, 512, and 1024. So these are good numbers, actually. And actually, another limitation that I didn't talk about is the maximum number of threads per block is actually limited by 1024. So you cannot have a thread block having 2048 threads. So these are pretty much often good choices. So this is one thing you might want to remember. But there's some remarks. So in the previous discussion, I'm only concerned about how many verbs you want to run, and you want to run, well, if possible, 64 verbs simultaneously. Because 64 verbs, so a single streaming multiprocessor can never go beyond 64 verbs, right? So the goal was running 64 verbs at the same time. But one remark is that 64 verbs is merely an upper bound. That may not be necessary to get the maximum performance. For example, so after all, all we need to get is the performance. For example, in terms of the floating point calculation performance. So the ultimate goal is not necessarily to get maximum number of verbs you are running at the same time, but to get the maximum performance. So in terms of whichever criteria that is important to you, like a floating point performance. For example, if you're doing floating point performance and try to maximize the floating point performance for your program, then the thing you need to try to accomplish is to execute 2 FMS every single cycle. So 64 FMS every single cycle. To accomplish this goal, but it is often useful, but not necessarily important. So it's not necessarily a requirement to run 64 verbs at the same time. So you simply determine the enough number of threads that can accomplish the goal of 2 verb FMS per cycle. The goal may be different depending on your applications. In some other cases, you might want to achieve the maximum memory access performance that is limited by the bandwidth of the hardware, the bandwidth of the GPU. Okay. And the other thing is, these 64 verbs may not be achievable due to other constraints. So for example, your computation uses so many registers and you allocate so much shared memory per block, then yeah, it becomes simply impossible to get enough thread blocks, which in turn means it is impossible to get 64 warps running at the same time. But in that case, well, it's simply whether the goal is somewhat different. So registers, unless you can easily reduce the number of registers or the shared memory size, well, it is the way it is in a way. So yeah, all in all, the takeaway I have just described in the last slide is simply a rule of thumb to eliminate obviously bad thread block sizes. For example, the thread block size of being 1 is almost always a bad choice. Likewise, 33 is probably almost always a bad choice. Something like this. So just if it is feasible to do so, just stick with these numbers. Okay. I got another question. So why the amount of shared memory is such a key value? So 164 is not power to. Yeah. So I don't know. I don't know why this particular choice, but they do not have to be necessarily a much block too. So that there's so many hardware that has a shared memory size or something else that is not about to. But I don't know what is the reason of this particular choice. All right, so yeah, this is the end of this thread block section. By the way, so lastly, so there's some interesting website that gives you a tool that calculates the number of warps that can run at the same time, given precisely the input that I have just described in the slide. For example, you specify the number of thread blocks, and you specify the model of the GPU. So 8.0 is the 800 you are playing with. And you also specify the registers per thread and shared memory per block. So these are essentially the 3 parameters you as a programmer effectively specify to the GPU and then calculate. It talks about the hardware limitations of GPU device. But the interesting thing is this. So you change the thread block size from 32, 64 all the way up to 1024. And this is the number of warps that are simultaneously running. So of course, it is at best 64. This is a hardware limitation. And you observe this interesting sort of zigzag pattern that stems from the fact that some thread block size, or equivalently some number of warps per block, does not divide the 64 without remainder. For example, this is 2 warps per block, right? So this divides the 64. So you get the maximum 64 warps. Similarly, this is 4 warps in a block, which again divides the 64. Then you get a 64 warps running at the same time. So for example, in the worst case, you see here, which is, I guess, so this is 20. So this is 21 warps. So this is 22 warps. So divide 64 by 22, then you get 2, right? Not 3. 22 by 3 is 66, slightly above 64. So you can only execute up to 2 threads at a time. So then you get only 44 warps running at the same time, right? So this is how this interesting pattern emerges. And this is precisely why the number of warps per block ought to be a divisor of 64. Okay. So maybe you find this too useful. Okay. So is there any question? Okay. So, well, I might give you some time for you to work on, any notebook you want to work on. So actually you get a new notebook called PD05 SIMD, not PL, so HL. So which I'm going to explain. So I didn't explain about this at all, but if you have done all other Jupyter notebook, you might just start reading it and start working on it. Otherwise, you can work on any Jupyter notebook you want to work on. So let's have something like 10 minutes for working on Jupyter notebook until 18, let's say 15. So exercise until then I start talking about the next topic. Okay, so let's get started again. So our next topic is this SIMD programming. Okay. Where's the pointer? Okay. Okay, so let's start talking about this SIMD programming. So here's some introductions. So what is SIMD? So it stands for Single Instruction Multiple Data, SIMD. So this is basically the way CPU, way CPU gets performance. So in terms of the execution platform, we come back to CPU. So again, from GPU. So this is the CPU thing. So a CPU, well, virtually all recent CPUs have this concept. So a processor has something called the SIMD registers, or equivalently called vector registers. So a single SIMD register or vector register can hold many values of a single type. So typically 2 to 16 values, or in some cases more. So like 16 single precision floating point numbers, or 8 double precision floating point numbers. So this is what single SIMD register typically is able to have. And there's SIMD instructions. So there's so many SIMD instructions, but a single SIMD instruction can apply an operation, for example, addition or multiplication, division, square root or something like that, on all or some values on a single SIMD register, or maybe multiple SIMD registers. So this is a simple illustration. So this is what a single SIMD register looks like. So I'm illustrating. So each box is a single, let's say 32-bit values, like floating point number. And a single SIMD register has 16 of them. And so when you need to distinguish many values in a single SIMD registers, a value in a so each value is called a SIMD lane, or simply a lane. So this SIMD register consists of 16 lanes. And actually this SIMD is a very indispensable tool for CPUs to get very good peak performance. So especially floating point performance. So as such, so this SIMD instructions are sort of evolving over time. So, but basically, so things are that this SIMD is kind of cheap or economical way to boost peak performance. So recent processors increasingly rely on the SIMD as an energy efficient way to get a better peak performance. So this is how the Intel processors evolve over time. So these are generations, so from one generation to next. And the most recent one is something called Ice Lake microarchitecture. And it has, also ISA stands for instruction set architecture. So because SIMD is basically about instructions, so the processor needs to extend its instruction set when you extend the capability, when you extend the capability. So this ISA evolves over time from something called SSE to AVX, AVX2, and most recently, something called AVX 512. By the way, 512 is the number of bits of a single SIMD register. And here you have something called the vector width of SP, it stands for single precision floating point numbers. So it used to be that a single SIMD register can have only 4 single precision floating point numbers. But nowadays, it is able to have 16 floating point, so single precision floating point numbers. By the way, so single precision floating point number is a 4 byte, which is 32 bits. So if you multiply 32 by 16, then you get 512, right? So this is the number of bits. And each of these processors can execute something like this in every single cycle. So the most recent generations typically are able to do SIMD FMAs. So he used to multiply and add instructions. And a single FMA is able to perform 16, a single SIMD FMA instruction is able to perform 16 FMAs, right? So in effect, so maximum number of single precision floating point operations per cycle is 64 in this generation, because so a single FMA instruction is able to execute 16 FMAs, which is 32 flops, right? So you count addition and multiplication each one as one, right? So a single FMA SIMD FMA instruction is able to perform 32 flops. And each cycle, the processor, the single core is able to execute 2 FMAs. So you get 32 multiplied by 2, so which is 64 flops per cycle per core. So this is how you get the peak flop of a machine. For example, having 2 Intel Xeon core this model and having 32 cores. So it is simply the multiplication of 64 flops per cycle with clock frequency, which is 2.1 billion clocks per second. So you also multiply it by 32 cores, and you finally multiply it by 2 sockets. So this machine is able to deliver something like 8.6 teraflops. But a large part of this performance, you can easily observe that a large part of this performance comes from this SIMD instruction, right? So if you hypothetically imagine you don't use SIMD instructions at all, then you get this factor of speed down, right? So you can only tap at the most 1/16 of single precision peak performance. Our machines having this AVX 512. So the important thing you have to remember is that machine is able to do SIMD FMAs per cycle. Does not mean, for example, if all these instructions are not SIMD instructions, so just instructions operating on the single floating point numbers, it's not that you are able to execute so many of them in a single cycle. So you still are only able to a couple of them in every single cycle, even if you do not use SIMD instructions at all. So in terms of the number of instructions you can execute at each cycle, SIMD versus non-SIMD do not make much difference. Which in turn means that in terms of the performance, using SIMD or not makes a huge difference. Because no matter whether it's SIMD or not SIMD, you can execute approximately the same number of instructions per cycle. So if you do not use SIMD at all, you simply waste so much of the execution resource of the CPU. So whenever SIMD is usable, you consider using it. So in this chapter and the accompanying notebook, you're going to learn how to actually use SIMD instructions, how to program the SIMD, so how to program SIMD, so how to write programs using SIMD. Well, to that end, of course, you do not necessarily have to learn how you actually write those SIMD instructions. So you want to stay at C level or high level programming language. But nevertheless, it is very useful and sometimes necessary to learn what actual SIMD instructions look like in the machine instruction level. Well, I come to the reason why you need to be able to at least understand what this instruction is doing. But yeah, for now, so this is what, for example, some instructions in this instruction set week0512F well actually looks like. So this is a multiply instruction that takes 3 registers. Its semantics is, so you multiply all the numbers in this SIMD register and all the numbers in SIMD register and put the result into this register. So this ZMM is a 512-bit register. So each of them can hold 16, either 16 single precision floating point numbers or 8 double precision floating point numbers. So 32-bit multiplied by 16 or 64 bits multiplied by 8. So either way, it's 512 bits, right? So this single instruction, SIMD instruction, will perform 16 multiplication, single precision multiplication. So similarly, this is an add operation. So which does this. And this is fused multiply and add operation, which is important when you talk about the peak performance. So to be precise, this is multiply these 2 numbers, 0 and 2, at ZMM1 and put the result to ZMM2. And actually, there are some other variations. So that are different in which operands are multiplied and which operand is added. So this is indicated by this mysterious number 132. So you get another variant like 213 or I don't remember. But basically, this indicates that you multiply the first one and the third one and add the second one. So this is how you remember. And there are memory access instructions, load instructions, and store instructions. So they actually having the same instruction names. Both are named move operations. So it takes the address that is in this register. So by the way, this is not a SIMD register. So this holds a single integer, which is an address. and it gets 512 bits from this address. So more precisely, whichever address that is in this register plus 256. So for example, this Rx has a value of 1024, then this instruction ends up accessing the address 1280, the address 1280. So 1024 plus 256. So get 64 bytes beginning from that address and get the value to this DML0 register. And this store instruction is the opposite. So you simply store this value, 64 bytes, into this address. Okay, so this is what the typical instructions look like. Yeah, of course, this is something you need to master. So in terms of how you actually program. So you actually do not write those instructions by yourself, typically, or free. But still, like I said, it is useful to be able to understand what the code generated by the compiler is doing. So that's why you need to have some knowledge about what the SIMD instructions actually look like. And so one point about these somewhat mysterious instruction names is that, okay, so the last two characters are actually important. So all these instructions have PS in common in the last two characters, right? And both P and S are important. So P stands for pack, which indicates this is a SIMD instruction. S stands for single precision. So PS means pack single precision instruction, which is essentially SIMD instructions operating on single precision floating point numbers. And to make things a little more complicated, this is definitely something fundamentally important, but still you sometimes need to know. So there are basically three kinds of registers in processors supporting AVX512. Well, largely for historical reasons. So the SIMD registers used to be called XMM, and in the earlier generation called SSE instruction set. And then in the next generation called AVX and AVX2, SIMD registers are called YMM. And in the latest generation, which is AVX512, they are called ZMM. They need to be named differently because their sizes are different, right? So XMM has only 128 bits. The YMM has 256 bits. ZMM has 512 bits. So on processors supporting AVX512, all these register names are available. But to make things a little bit tricky, it's not that you have all distinct registers, some number of XMM registers, some number of YMM registers, and others named ZMM registers. Well, actually, XMM, YMM, and ZMM with the same numbers at the end will share part of it. So it's most basically the last 256 bits of ZMM 13 is actually YMM 13. And the last 128 bits of either ZMM 13 or YMM 13 is actually XMM 13. So they are in a way aliased. So it's not that the total number of registers you have is 16 plus 16 plus 32. So you only have 32 registers. But this is one thing you might want to remember, just so that you are not confused at times. And just as you have many kinds of slightly different SIMD registers, you have slightly different instructions doing logically the same thing. And you need to be able to distinguish between one version to another to know whether the compiler was actually able to use particular SIMD instruction set. So the thing you need to remember is that, like I said, the last two characters are important. And when the second last character is P, it means they are SIMD instructions. So P stands for packed. So packed are so many values packed into a single register or a single instruction. So those are SIMD instructions. So the last 6 instructions are SIMD instructions. But you have a variant of instructions having SS or SD in the last 2 characters. So that if the second last character is S, it means it is a scalar instruction. So it is not a SIMD instruction at all. So that's why you need to be, well, somewhat careful, especially because they all look very similar in instruction names, but what they are doing is very different. So like I said, whether this is a SIMD instruction or not, it is a big deal, right? So you at least need to remember the second last character is either S or P, and whether it is P or S makes a significant difference in terms of what it is doing, and also for performance. Okay, so with that, I think we need to finish for today. And so so in the next week, I continue explaining this SIMD thing, and hopefully you guys have some time to work on this notebook. And in this notebook, so you will be doing something slightly different from previous notebooks. So you write what you observe in a shared Excel sheet. This is what the Excel sheet you will be going to work on. So make sure that you are able to access this notebook, and so Excel sheet, just by clicking this. And to access this Excel notebook, Excel workbook, you need to be able to sign in Microsoft using University of Tokyo account. So 10-digit number followed by @utaq.tokyo.acg.jp. So if you have never done signing in Microsoft account using Utopia account, make sure you have done this. And if you do not know how, then check this page. But by the next week, yeah, I'll encourage to make sure that you can access this workbook. So with that, I think we are done for today.